Morning. So, in the last class, we already discussed about the linear convolution and circular convolution, right? So, linear convolution in two methods we observed. Linear convolution, two methods we observed. So, linear convolution overlap add method and overlap save method. In overlap save method also we have two methods. First method and in first method one. And for the last section, we have zeros will be appended and uh, in the second method zeros will be appended in the first first section. Okay, so that is the overlap save method, right? So next, coming to the circular convolution. So circular convolution we already discussed in the last class. So circular convolution, for doing the circular convolution, so the length of the two sequences will be same. The length of the two sequences will be same. Here the given length of the x1 of n is 5 and second one is 3. So make it as 5. The length of the second sequence will be also 5, so that zeros will be added. So 1, 2, 3, 0, 0. So here we have two methods are there. First one is concentric circle method and second one is matrix multiplication method. In concentric circles method, here we will take two circles, outermost circle and innermost circle. Okay, so the outermost circle will be in counterclockwise direction. Here the elements will be in counterclockwise direction, and innermost circle will be clockwise direction. See here, x1 of n is given as 1, minus 2, 3, and minus 1. Okay, and x2 of n is given as 1, 2, 3, 0, 0. Right. So here the outermost circle will be counterclockwise. Counterclockwise means it is in anti-clockwise direction. Okay, anti-clockwise direction. So he see here it is x1 of 0, that is 1. Next x1 of 1, that is minus 1. The next x1 of 2, that is that is that is x1 of 2 is minus 2. Like that, it will be arranged in counterclockwise direction. Okay, and then second one is inner circle is clockwise direction. Here the values are 1, 2, 3, 0, 0. This is x2 of 0, x2 of 1, x2 of 2, x2 of 3, x2 of 4. This will vary in clockwise direction. So this is x1 of 0. Next x1, this is x2 of 0, x2 of 1. Okay, x2 of 2, x2 of 3, x2 of 4. Like that, it will be arranged. Okay, 1, 2, 3, 0, 0. Right. So then first we have to multiply these two multiply corresponding samples on the circle and add
Recording in progress.
to obtain y of 0. Okay, y of 0. Right. See by multiplying these two, 1 into 1 plus minus 1 into 0, minus 1 plus minus 2 into 0, that is 0, plus 3 into 3, 9, plus 1 into 2, minus 1 into minus 2. Okay, like that, we will multiply these elements so that we will get y of 0. How to get y of 1, y of 2, y of 3, y of 4? So y of 1 will be obtained by rotate the inner circle in a counterclockwise direction by one sample, multiply the corresponding samples to obtain y of 1. So see here, this is the inner circle. So inner circle will be rotated by counterclockwise direction, that is anti-clockwise direction, by only one sample. So that it will be turned counterclockwise direction, anti-clockwise direction. One will go to here. So this is 1, 0, 0, 3, 2, like this. And then the outermost circle elements will not be changed. Only inner circle will be rotated in counterclockwise direction by one sample, so that we will get y of 1. Then multiply these two, 1 into 2, plus minus 1 into 1, plus minus 2 into 1, 0, plus 3 into 0, plus minus 1 into 3, so that we will get y of 1. In the same manner, so how to get y of 2? Rotate the inner circle by inner circle in counterclockwise direction by one sample, so that we will get y of 2, and then y of 3, and then y of 4. Like this, we will get y of n as y of 0, y of 1, y of 2, y of 3, y of 4, like 8, minus 2, minus 1, minus 4, and minus 1. This is one method of doing the circular convolution. Next method is matrix method. Okay. Okay, so given x1 of n is 1 minus 1 minus 2 3 minus 1, and x2 of n is 1 to 3, we will add 2 zeros, so that the length of the two sequences will be equal. Okay, now the matrix form can be written as x2 of n into x1 of n is equal to y of n. What is x2 of n? 1 2 3 0 0. What is x1 of n? 1 minus 1 minus 2 3 minus 1. So x1 of n will be written as it is, that is 1 minus 1 minus 2 3 minus 1, and x2 of n will be written as in this manner. So this manner is x2 of 0, x2 of 1, 2, 3, 4, and this 4 will be written at here. Then this will be repeated, x2 of 0, 1, 2, 3. Then this x2 of 3 will be written at here. Okay. Then x2 of 4, x2 of 0, x2 of 1, x2. Then x2 of 2 can be written at here. Then x2 of 3, x2 of 4, x2 of 0, x2 of 1. Then x2 of 1 can be written at here, x2 of 2, x2 of 3, x2 of 4, x2 of 0. Like this, in this manner, the second matrix will be written. Okay, the second x2 of n sequence will be written. It is okay. See here. See, so this is given as 1 2 3 0 0, 1 2 3 0. This 0 will be written at here. Then 1 2 3 0. This 0 will be written in here. Okay, 0 0 1 2 3. 3 will be written here. 0 0 1 2. 2 will be written at here. 3 0 0 0 1. Like this. Then we will do the multiplication of these two, so that we will get the y of n is 8 minus 2 minus 1 minus 4, and minus 1. So this is the another method of doing the circular convolution, that is matrix method. Matrix method. Okay, matrix method. Next, in the same manner, we can find the circular convolution of two sequences. X1 of n is given as 1 2 2 1, and x2 of n is given as 1 2 3 1, using the concentric circle method and matrix method. So here the length of the two sequences will be same, 4 only. So no need to add zeros, or no need to delete zeros here. So directly we can do the matrix circular convolution by using concentric circle method as well as matrix method, right? You can do this problem. Note down this and do this one. X1 of n equal to 1 2 2 1, and x2 of n equal to 1 2 3 1, right? So you may get the result of y of n is 11 9 10 12. 11 9 10 12. Note down this and do this one. Next, problem number 3 is perform the circular convolution. Perform the circular convolution. Circular convolution of the following sequences. So here x of n is given as 1 1 2 1, and h of n is given as 1 2 3 4, using DFT and IDFT method. What is meant by DFT? Discrete Fourier transform. What is meant by IDFT? Inverse discrete Fourier transform. DFT is discrete Fourier transform. So for doing discrete Fourier transform and inverse discrete Fourier transform, we have the formulas. What is the formula for doing the discrete Fourier transform? That is x of k is equal to sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n, where k is varying from 0 to n minus 1 or k is in between 0 to n minus 1. Okay, so this is the formula for doing the discrete Fourier transform. And what is the formula for doing the inverse discrete Fourier transform? That is 1 by, this is the formula for doing the discrete for inverse discrete Fourier transform. That is x of n equal to 1 by n into sigma k equal to 0 to n minus 1 x of k into e power plus j 2 pi k n by n for n equal to 0 to n minus 1 or n is in between 0 to n minus 1. Okay. So here we have to do the circular convolution of the two sequences using DFT and IDFT. So first of all, we will do the DFT, and after that we will do the IDFT. Okay. So the convolution, as we already know that the convolution in time domain will become simple multiplication in frequency domain, right? Convolution in time domain will become simple multiplication in frequency domain, as we already know that. Okay. So here also we are applying the same concept, that is suppose x3 of k is the resultant. So x3 of k is nothing but multiplication of x1 of k and x2 of k. Here x2 of k is h of k, right? x1 of k into, or x of k into h of k, right? Okay, right. First of all, we will do the x1 of k. This x1 of k, this or x of k. So sigma n equal to 0 to n minus 1 x1 of n into e power minus j 2 pi k n by n, where k is varying from 0 to n minus 1. Okay. Here x1 of n is 1, 1, 2, 1. Here n is the length of the sequence is 4. So n equal to 0 to 4 minus 1, that is 3. N equal to 0 to 3 x1 of n into e power minus j 2 pi kn by n. N is 4. Okay, so for x1 of 0, here if n is 0, then x1 of n into e power 0. E power 0 is 1. So that it will become x1 of 0 plus x1 of 1 plus x1 of 2 plus x1 of 3. So these are the values given. So it is x1 of 0, you will get the x1 of 0 value is 5, right? Similarly, x1 of 1, that is x1 of 1 into, okay, n is if n is 1, so x1 of 1 into e power minus j 2 pi kn by 1, kn by 4. So k value is 0 to 0 to 3. Here also n value is 0 to 3. So by simply substituting those values, we will get x1 of 1 is minus 1. Similar in the same manner, x1 of 2 is 1. x1 of 3 is minus 1. Therefore, x1 of k is 5 minus 1, 1 minus 1. This is x of k, right? Next, in the same manner, we will do the h of k. H of k, that is x2 of k. Let us take it. This is x2 of k. So here also the length of the h of n is 4. So it is k is varying from 0 to 4 minus 1, that is 3. Similarly, n is also varying from 0 to n minus 1, that is 3, 0 to 3. So that here also we will get x2 of 0, x2 of 1, x2 of 2, and x3 of 2, x2 of 3. Like this, these are the values. x2 of 0 is 10, x2 of 1 is minus 2 plus j2, x2 of 2 is minus 2, x2 of 3 is minus 2 minus j2. So finally, x2 of k is 10, minus 2 plus j2, minus 2, and minus 2 minus j2. So simply substitute multiplying these two values, x1 of k and x2 of k. This x1 of k is nothing but x of k. This x2 of k is nothing but h of k, right? So by simply multiplying these values, we will get x3 of k, that is the its response is 10 into 5, 50, minus 1 into 2 minus j2, that is minus 2 plus j2, 2 minus 2 plus j2, and 1 into minus 2, that is minus 2, and minus 1 into minus 2 minus j2, that is 2 plus j2, right? So this is DFT. Then coming to the inverse DFT, that is x3 of n equal 1 by n into sigma k equal to 0 to n minus 1, x3 of k into e power plus j pi to j pi into kn by n, for n is varying from 0 to n minus 1. The same manner, x3 of 0, 1, 2, 3. So we can substitute these values. So x3 of 0 is 13, x3 of 1 is 14, x3 of 2 is 11, and x3 of 3 is 12. So finally, x3 of n, that is inverse discrete Fourier transform x3 of n is equal to 13, 4, 11, 12. Okay, this is about the circular convolution using DFT and IDFT. The above one is circular convolution using concentric circles method and matrix multiplication method, right? Okay, so this is about the DFT, right? So next coming to the fast Fourier transform. Fast Fourier transform. So far we discussed about the discrete Fourier transform and its properties and inverse discrete Fourier transform, etc. Right? And linear convolution, circular convolution, etc. The last topic in this unit is fast Fourier transform. So this is the advanced version of the discrete Fourier transform. So what is fast Fourier transform? Suppose if you take discrete Fourier transform, it can be used to perform linear filtering. Okay, it is used to perform, it can be used to perform linear filtering. Okay, set of algorithms known as fast Fourier transform proposed by Cooley and Tuckey in 1963. So a set of algorithms known as fast Fourier transform. This is proposed by Cooley and Tuckey. These are the named after the scientists Cooley and Tuckey in 1963. So FFT is a highly efficient procedure for computing the DFT of finite series and requires mainly it requires less number of computations than that of the discrete direct evolution of discrete Fourier transform. So FFT requires less number of computations when compared with the DFT, right? It is based on decomposition and combining them to get the total transform. First of all, we will decompose it and again combine. So FFT is based on this principle. Okay, principle. So FFT is based on decomposition and combining them to get the total transform. Why this FFT is needed? So direct evaluation of DFT using the formula x of a equals sigma n equals 0 to n minus 1 x of n and e power minus j 2 pi n k by n requires n square complex multiplications, n square complex multiplications, and n into n minus 1 complete additions. Okay, n into n minus 1 complete additions, right? So thus for large values of n, suppose if n is larger, so it is not possible. We have to square it and n square complex multiplications and n into n minus 1 complex additions. So DFT requires n square complex multiplications and n into n minus 1 complex additions. If n is larger one, this is not possible. So by using FFT algorithm, the number of computations can be reduced. Okay, number of computations can be reduced. Okay, suppose if you take the direct evaluation of DFT, that is x of k is equal to sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi n k by n, where k is varying from 0 to n minus 1. Let it be considered as equation number 1. Here e power minus j 2 pi by n, this e power minus j 2 pi by n will be replaced by Wn, W suffix n. Substituting Wn is equal to e power minus j 2 pi n. So substitute Wn equal to e power minus j 2 pi n in the equation number 1. So replace e power minus j 2 pi by n is Wn. So that x of k will become sigma n equal to 0 to n minus 1 x of n into Wn power nk. Why? Because e power minus j 2 pi by n is nothing but Wn. For k is varying from 0 to n minus 1. Let it be considered as equation number 2. Okay. Now we will write this x of n and Wn power nk as sum of the real and imaginary terms. Okay. Okay. Sigma n equal to 0 to n minus 1 real part of x of n plus imaginary part of j into imaginary part of x of n into real part of Wn power nk plus j into imaginary part of Wn power nk. Multiply these two. Okay, multiply these two braces. This is considered as equation number 3. Now multiply these two, that is sigma n equal to 0 to n minus 1 real of x of n into real of Wn whole power n plus sigma n equal to 0 to n minus 1 j imaginary of x of n into real of Wn power nk plus sigma n equal to 0 to n minus 1 j into uh, real of x of n into imaginary of w n power n k minus j square j into j square into im into sigma n equal to 0 to n minus 1 im into x of n into im into w n power n k. So j square will become minus 1, that's why it is minus. Okay, now we will write real terms into one side and imaginary terms into another side. Okay, it is equal to sigma n equal to 0 to n minus 1 real of x of n into real of w n for n k minus sigma n equal to 0 to n minus 1 im into x of n imaginary of x of n into imaginary of w n power n k plus j into sigma n equal to 0 to n imaginary of x of n into real of w n power n k plus sigma n equal to 0 to n minus 1. Okay, 0 to n minus 1 real of x of n into imaginary of w n power n k, right? So understood. Okay, here we are writing this x of n into w of n power n k as a combination of real and imaginary terms. So real of x of n plus j into imaginary of x of n into real of w n power n k plus j into imaginary of w n power n k, right? Now uh, multiply these two so that we will write real terms into one side and imaginary terms into another side, so that we will get this equation, that is this equation here where this wn is considered as fiddle factor. Wn is called fiddle factor. Wn is called fiddle factor. Okay, now equation number 3, we can evaluate one value of x of k. Okay, from equation number 3, we can evaluate one value of x of k. The number of complex multiplications required is n. To evaluate all n values of x of k, the number of complex multiplications required is n square, and the number of complex additions required is n minus 1. Okay, so to evaluate all n values of x of k, the number of complex additions required is n into n minus 1. So direct evaluation of DFT is basically inefficient because it does not use the symmetry and periodicity properties of the fiddle factor Wn, right? So it is inefficient. Direct evaluation of DFT is inefficient because of it does not use the symmetry and periodicity properties of fiddle factor Wn. These two properties are if we take symmetry property, that is Wn power k plus n by 2 is equal to minus Wn power k, and the periodicity property is Wn power k plus n is equal to Wn power k. So here these two are the fiddle factors properties, that is symmetry property and periodicity property. What is symmetry property? Wn power k plus n by 2 is equal to minus Wn power k, right? Minus Wn power k. Similarly, periodicity property is Wn power k plus n equal to Wn power k. So DFT, direct discrete Fourier transform, is inefficient because of it does not have the periodicity and symmetry properties of fiddle factor. That's why we will go for the fast Fourier transform. By using the fast Fourier transform, here we can reduce the number of computations. The number of computations will be reduced when compared with the direct evaluation of discrete Fourier transform. In FFT, the number of computations will be reduced when compared with the direct evaluation of discrete Fourier transform, right? Right. So now coming to the FFT, fast Fourier transform. So it exploits two basic properties of fiddle factor and reduces the number of complex multiplications required to perform DFT from n square. So here in DFT we have the multiple. So we have the complex multiplication n square. N square is there. N square in DFT it can be replaced by n by 2 into log n to the base 2. Okay, in FFT n square is replaced by n by 2 log n by 2, log n to the base 2, n by 2 log n to the base 2. Suppose, for example, if you take n is 64, 64 point sequence is there. Okay, in DFT it can be written as n square. N square means 64 whole square, that is 4096. Whereas in FFT it can be written as n by 2 log n to the base 2. N is 64, so 64 by 2 log 64 to the base 2, so it can be uh, evaluated as 192. It is 4096, it is 192. Like this, we have the number of competitions will be reduced in FFT when while compared with the DFT. Number of competitions will be reduced and compared with DFT. Okay. Right. Next. So this is the advantage of FFT. Okay, here the number of competitions will be reduced when compared with the direct evaluation of DFT, right? Number of competitions will be reduced. See this example. So 64 point sequence is there. In DFT it is 64 square n square, whereas in FFT it is n by 2 log n to the base 2, that is 192. So next, coming to the two classes of FFT algorithms. Here we have two classes of fast Fourier transform algorithms. That is, first one is decimation in time. Decimation in time FFT. Next one is decimation in frequency FFT. Decimation in time FFT, that is called DAT FFT. DAT FFT. Decimation in time FFT. Okay, that is DAT FFT. Okay. Next, decimation in DAF FFT. Decimation in frequency FFT. Now we will see the DAT FFT. Decimation in time FFT. Right. So this algorithm is also known as radix 2. Radix 2 DAT FFT. Radix 2 DAT FFT algorithm. So the number of output points n can be expressed as n equal to 2 power m minus m integer. Okay. Right, 2 power m minus m integer. Let x of n is n point sequence, same, where n is assumed to be power of 2. Okay, decimate or break this sequence into two sequences of length n by 2, where one sequence consisting of even indexed values of x of n and the other of odd indexed values of x of n. So x of n with the sequence n can be divided into two sequences. One is considered as even indexed sequence, and the other one is odd indexed sequence. That is XE of n. XE of n equal to 2n, where n is varying from 0 to n by 2 minus 1. Okay, and XO of n, x odd of n, x even of n, x odd of n, it is equal to 2n plus 1, where n is varying from 0 to n by 2 minus 1. Let it be considered as equation number 1. So n point DFT of x of n can be written as, so x of k equal to sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi nk by n, like DFT, right? Right. So this is sigma n equal to 0 to n minus 1 x of n and e power minus j 2 pi by n is written as wn. So wn power nk, that is equation number 2, where e power minus j 2 pi by n is equal to wn, where k is varying from 0 to n minus 1, right? 0 to n minus 1, right? 0 to n minus 1, that is equation number 2. Okay, so here we are writing this x of k as a combination of even indexed values and odd indexed values, right? Even indexed values and odd indexed values. Separating x of n into even and odd indexed values of x of n, we obtain x of n equal to sigma n equal to 0 to n minus 1 x of n into wn power nk plus sigma n equal to 0 to n minus 1 x of n into wn power nk, right? wn power nk. Okay, right. Here for even indexed sequence, replace n by 2n, and for odd indexed sequence, replace n by 2n plus 1, right? In equation number 1 we represented, right? So for even indexed sequences, xe of n equal to 2n and xo of n equal to x odd of n equal to 2n plus 1, right? So here replace n by 2n and here replace n by 2n plus 1, so that it will become n equal to 0 to n by 2 minus 1 x of 2n into wn of n is replaced by 2n, 2nk plus sigma n equal to 0 to n by 2 minus 1 into x of 2n plus 1. This is odd index sequence. So 2n plus 1 into wn of 2n plus 1 into k, right? So it is equal to sigma n equal to 0 to n by 2 minus 1 into n by 2 minus 1 into, okay, x of 2n into wn for 2nk plus sigma n equal to 0 to n by 2 minus 1 into x of 2n plus 1 into, this can be written as wn of 2nk into wn of k. Okay, this can be extracted outside wn of k, okay, into sigma n equal to 0 to n by 2 minus 1 x of 2n plus 1 into wn of 2n plus 2nk. That is, let it be considered as equation number 3. Okay, right. So we can write this as sigma n equal to 0 to n by 2 minus 1 into xe of n. X of 2n is nothing but xe of n, right? So xe of n is x of 2n. So and xo of n is x of 2n plus 1, right? So this x of 2n can be replaced as xe of n into wn for 2nk plus wn for k into sigma n equal to 0 to n by 2 minus 1 into x of 2n plus 1 can be replaced by xo of n into wn of 2nk, right? Let it be considered as equation number 4. Now we can write wn of 2, wn as e power minus j 2 pi by n whole square, right? Okay, so we can write this as e power minus j 2 pi by n by 2, e power minus j 2 pi by n by 2, or this is wn by 2. So wn power 2 is equal to wn by 2. This is equation number 5. Observe it. Wn power 2 can be written as wn by 2. Why? Because wn is e power minus j 2 pi by n, right? Whole power 2. This power 2 can be written like this: e power minus j 2 pi by n by 2. Okay, that is wn by 2, right? Wn by 2. So wn square can be written as wn by 2. Let it be considered as equation number 5. Now replace wn square as wn by 2. Okay, so this can be written as the above equation can be written as equation number 4 can be written as sigma n equal to 0 to n by 2 minus 1 xe of n into wn square can be written as wn by 2 whole power n k plus wn power k into sigma n equal to 0 to n by 2 minus 1 into xo of n into wn by 2 power n k, right? So this first part is n by 2 point DFT of even indexed sequence, and the second part is n by 2 point DFT of odd indexed sequence. So we can write this as x of k equal to capital xe of k plus wn power k into capital xo of k. That is even symmetry. Okay, this will be considered as equation number 7. So this is even symmetry, right? So where k is varying from 0 to n minus 1, or k is in between 0 to n minus 1. For n by 2 sequence, k ranges from 0 to n by 2 minus 1, right? For n sequence, it is varying from n minus 1. Okay, this is n by 2 sequence, that's why it is varying from 0 to n by 2 minus 1. So for n k is greater than or equal to n by 2, for k is greater than or equal to n by 2, wn for k plus n by 2, wn for k plus n by 2 is nothing but minus wn power k minus wn power k. This is nothing but symmetry property. Symmetry property. Okay, so that is equation number 8, symmetry property. Now x of k for k is greater than or equal to n by 2 is given by x of k equal to xe of k minus, this is plus wn power k. So if wn power k plus n by 2 is minus wn power k, so this can be replaced by xe of k minus n by 2, x of k equal to xe of k minus n by 2 minus w n power k minus n by 2 into by 2 into x naught of k minus n by 2 for k equal to n by 2, n by 2 plus 1 up to n minus 1. Right, let it be considered as equation number 9. Okay, using symmetry property, this x of t can be replaced by xe of k minus n by 2 plus uh, minus wn of k minus n by 2 into xo of k minus n by 2. So this k is replaced by k minus n by 2, right? Using symmetry property, right? So for direct evaluation of DFT, let us take n is 8, then n by 2 is 8 by 2, that is 4. So when n equal to 0, then xe of n is 2n and x naught of n is 2n plus 1, 2n plus 1. Okay, 2n plus 1, right? 2n plus 1. So xe of n is 2n and x naught of n is 2n plus 1. 2n plus 1, right? So when n equal to 0, then xe of 0 is 2 into 0, that is 0. When n is 1, that is 2. If n is 2, that is 2 into 2, 4. When n is 3, that is 6, right? So this is a even part of even indexed even indexed sequence. X naught of n equal to 2n plus 1. So when n equal to 0, this is 1. N is 1, this is 3. N is 2, this is 5. N is 2, this is 7. So from equation number 7, so what is equation number 7? So that is x of k is equal to xe of k plus wn of k into wn power k into x naught of k. So xo of k, that is so x of k equal to xe of k plus wn power k into x of k for 0 is less than or equal to k is less than or equal to 3. Let it be considered as equation number 10. From equation 9, we have x of k equal to symmetry property. So that is xe of k minus n by 2 minus wn of n power k minus n by 2 into xo of k minus n by 2 for 4 is less than or equal to k is less than or equal to 7. That is the equation number 11. By substituting different values of k in equation number 10 and equation number 11, we get k. What is k? K is varying from 0 to 3. K equal to 0 to 3. And here k is 4 to 7. So substituting these 0, 3 values in equation number 10, we will get x of k equal to xe of k plus wn power k into x now xo of k. If k is 0, then x of 0 equal to xe of 0 plus w n value is 8, w 8 power 0 into x o of 0. If k is 1, then x of 1 equal to xe of 1. Okay, xe of 1 xe of 1 plus w for 1 into x o of 1. X of 2 equal to xe of 2 plus w for 2 into x o of 2, and x of 3 equal to xe of 3 plus w for 3 into x o of 3. Similarly, by substituting the values of k from 4 to 7 in equation number 11, so that we will get x of k is equal to xe of k minus n by 2 minus wn power k minus n by 2 into x o of k minus n by 2. So that if k is 4, then we will get x of 4 equal to xe of 0 minus w for 0 into x o of x o of 0. If k is 5, we will get x of 5 equal to xe of 1 minus w for 1 into x o of 1. Okay, and if k is 6, it is xe of 2 minus w8 for 2 into xo of 2. If k is 7, then it is xe of 3 minus w8 for 3 into xo of 0. From the above set of equations, we can find that x of 0 and x of 4. Similarly, x of 1 and x of 5, x of 2 and x of 6, x of 3 and x of 7 have same inputs. Okay, x of 0 is obtained by multiplying x0 of 0 with the w8 for 0 and adding the product to xe of 0. Similarly, x of 4 can be obtained by multiplying XO of 0 with the W840 and subtracting this product from XE of 0. Okay, this operation can be represented by a butterfly diagram. This is called butterfly diagram. So A is given as XE of 0 and B is given as XO of 0. Okay, write the butterfly model. Uh, Draw the butterfly model, and this is fiddle factor W8 power 0. So XE of 0, how to get this output? A plus W840 into B. What is A?